Probability is a very mathematical topic in statistics. But don't worry, we're going to break down each equation and how to use it. But let's first talk about what a random phenomenon is. But when we have a random phenomenon, the best thing to think about is a coin flip. In the coin flip, you understand the distribution of what can happen, heads or tails. But when you flip the coin, you don't know what will happen next, so it's kind of a random phenomena of what will happen. If you flipped the coin 4 times and you got heads, 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 how unusual is that? Do you think you might get heads another time in a row? Is it more or less likely? We'll examine those ideas here in this lecture. Let's first look at some key terms though. Flipping the coin itself is known as a trial. If you see a word in red, write it down, put it on a note card. A trial is just when we run the outcome or try to achieve an outcome of doing a random phenomena. Once again, flipping the coin would be the trial. And I already said it, an outcome is when the coin actually lands and you see what it is. So maybe you buy a lottery ticket, that's the trial, and then when you see if you win or lose, that's the outcome. Now when we combined events together, we can look at, or combined outcomes together, we can look at an event. So the event of winning the lottery twice in a row, that'd be extremely rare. The event of getting 10 heads in a row. The event of your team winning 3 times in a row. The event of your team losing and then winning 2 games in a row. All of these things are possible, and we need to think about what could happen in a sample space. And a sample space, which is not a sample frame, is all possible outcomes. A very easy sample space to think about is coin flips. Coin flips, so heads, tails. If someone wanted to get really crazy, they could say edge of coin. I wonder if anyone's ever flipped a coin that's truly landed on its edge. But that is extremely unlikely, and it probably just means you reflip the coin. If you get a valid coin flip, we could say this, a valid coin flip has the sample space heads or tails. When you think about a football game, what is the sample space of a football game? Now we would get into win, lose, or tie. Because there's 3 possible outcomes that could happen that we are thinking about here as the outcome of a football game. Some sports don't have ties though. You either win or you lose. Let's think about this. If your team plays 2 games, what is this possible outcomes of 2 games? So you have the first game and then the second game. So the sample space here would be something like you either win the first, win the second, you win the first, you lose the second, you lose the first, you win the second, you lose and lose. Think about this. This is all possible things that could happen. We color code a little bit more so you can see. Win 2 times in a row. Or we have that you win the first, lose the second, lose the first, win the second, lose the first, lose the second. These are all things that could occur, and we could look at the probabilities of these different things in mathematics. Another key term here is independent. And coin flips are your perfect example of what is independent. Try to write down examples, try to remember like a coin flip is independent. What does that mean? When I flip the coin, previous coin flips have no influence over it. Independent means if you know one thing, the thing number 1 over here, it tells you nothing about thing number 2. It does not give you any information. So if someone says, oh, that coin just flipped tails, you'd be like, okay, thank you. That's not going to help me figure out what's going to flip next. But think about this. If somebody told you, let's say, they said that this is a rigged coin. They said this is a rigged coin. It's a weighted coin. And they said it flips heads. It's a weighted coin that flips heads. Would that be independent of what this coin flips over here? Thing number 2. Thing number 1, they tell you it's a rigged coin. Now what the coin flips, is that going to be independent of that information? No. This coin is probably extremely likely to flip heads because the information tells you something about what will happen. I always like to use examples like this too, where I say, drinking coffee in the morning. So my brother, over here, Darren, and here's me. Now, Darren and I don't talk each morning. You might say, well, you grew up together, so you are maybe going to drink coffee because your brother drinks coffee growing up. That's one way to look at it. But let's go at current point in time. Brian drinks coffee 90% of mornings. Darren drinks coffee 80% of mornings. So with this information, you kind of know, generally speaking, Brian drinks coffee a little more often than Darren. Darren doesn't drink coffee as much as Brian. So if Darren doesn't drink coffee, we don't live together, we don't talk every morning, would that influence Brian to change his coffee habit? Would Brian be influenced by Darren drinking coffee? No, because Darren doesn't influence Brian, so this would be a good example of independent right here, because knowing Darren drank coffee would not influence your opinion about Brian drinking coffee. But if we were to talk about my wife, and she probably drinks coffee 99% of mornings, you might say, well, Brian drinking coffee and his wife drinking coffee are dependent. Why is that? Well, we use the same coffee machine. So if you knew my wife did not drink coffee, you might be like, well, maybe Brian didn't drink coffee because maybe something's going on. Maybe they ran out of coffee right there. It would influence. So me drinking coffee somewhat depends on my wife drinking coffee. Maybe we woke up and I forgot to make a pot of coffee and there was no coffee. There could still be coffee, but with this in mind, think about what dependent means. That if you know one thing over here, Brian's wife did not drink coffee, does that then influence your opinion in some way of this other one? You're like, well, I think it's less likely Brian drank coffee. So Brian drinking coffee is some way dependent on his wife drinking coffee. Now, if this is too complicated, think about a much simpler example. Studying and your grades. If you know somebody studied the night before a test, would that influence what you think about their exam grade? You look at thing one, and yes, does it influence my view on thing two? And if it does, they are not independent. And this would be another example of not independent, also dependent. And then say it out loud. Be like, someone's exam grade depends on if they study. That makes perfect sense. Not independent can be said too, like someone's exam grade is not independent of how much they studied. Keyword right here, independent, and it's going to be very important to use later on. Let's talk about the law of large numbers. Now, this is a law, as in, it is always true. It cannot be broken. If you were to walk out to a red light in your neighborhood and see at a random time if it's green or red, not always a red light, right? The first time you walk up, it's green. The next time you walk up, it's red. The next time it's green, it's red, it's red. And look what happens to the graphic. The first time it's 100% green because that's all the information you have. Then it starts to even out and get less jittery, we should say. Because as you get more observations, you actually start to approach the truth. And we don't know exactly what the truth is, but we would have more certainty that we're closer to the truth with a larger sample size. And in the beginning, you get that quick kind of up-down, and then it starts to level off. We could also make confidence intervals later on to get a better estimate of what the truth might be. But the law of large numbers states, over the long frequency of observing an event, you will see the true probability. And these need to be independent, where you don't just walk out there and record red, 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 because then the light color in the second one is very dependent what it'll be 1 second later. You should go at different random times and record then, and you'd have independent trials right there of viewing an event. So independent trials of viewing an event over the long run will show the true probability, and that is called the law of large numbers. But there is the law of averages, which is a fallacy. A fallacy means improper thinking. Now, you could possibly be right by doing fallacious thinking, but likely it'll lead to more errors in the long run than truths like the law of large numbers. So you could call this instead the fallacy of averages. Not the way things work. It's like when somebody flips a coin, it goes heads, heads. And you know this is a fair coin. We're not using an unfair coin right here. And they say, well, it just flipped heads 2 times in a row. It's due to flip tails. Like, that's not how coins work. And then they flip tails and they're like, see, I told you. I said it was due to flip tails. Well, they had a 50-50 shot. Say, okay, let's get 3 heads in a row. And then I want to go with you. I want to go a 10-to-1 wager every time. 10-to-1, meaning if I bet $10 and they're wrong, they have to give me 100. I'll just give them the 10. So we'll say, we'll flip, I'll let you get 5 in a row of something, 5 tails in a row. And then we'll go 10-to-1 on the next flip. If they take those odds, don't be too mean to your friends. But if it's truly a fair coin, they're going to start losing money very quickly, and they'll realize that the law of averages is not true. It's a fallacy. These graphics right here show it. And you have to think, what exactly am I looking at? Well, the top one shows you the ratio of how many heads there are to how many tails there are when you flip a coin. In this, you start out that you at first, it looks like, have only one more heads to tails. Then you get a few more tails, you're more on the heads, you're more on the tails, you go way more on the tails, more on heads, because this is like you're off by this many. After 1,000 coin flips, you're off by like 20 extra tails. If it's negative, there's been a few more tails than heads. After 5,000 tails, or 5,000 flips, you are over by about 22 heads, because the positive would here be too many heads. You have like 22 more heads in your coin flips than tails. Shouldn't it be a 50-50 coin flip? Well, after 5,000 coin flips, 22 extra on one side is nothing. And if you look at the law of large numbers down here, it shows you the coin is perfectly almost 50-50. You're always going to have a little bit extra or a little bit off because it's never perfect, and you just get better and better estimates as you get more data. And think about this. Being 10 off when you do 20 coin flips would be pretty crazy. That'd be all 20 heads. But being 10 off with 5,000 coin flips would be nothing. It'd be 4,000 or 2,455 or 2,495 to 2,505, which is fractions of a difference. So people would be like, well, it had more heads than tails. You'd be like, but 50-50, it's approaching it in the long run due to the law of averages on the bottom graphic. Once again, the key thing to know right here is the law of averages is a fallacy. I call it the law of the fallacy of averages. The law of large numbers is the truth that in the long run frequency of independent trials, we will see the true probability of an event. Now let's get to some of the mathematics right here with modeling probability. So we love games of chance and statistics. Card games, dice rolls, roulette wheels, things like that are great for understanding probability. Now, people have subjective or personal probabilities, like my team has a 70% chance of winning tonight. They're not using the long run frequency of events, and we shouldn't really use subjective or personal probabilities because we can't really do formal mathematical probability with them. So when can we use this right here? Well, the easiest way to do it is when things are equally likely. When you think about it, every lottery ticket has an equal and likely chance of winning. We're talking about all combinations of lottery ticket numbers. You write them all down, the sample space of every single lottery ticket. You've got lottery ticket 1, 2, 3, 4, 5, 6. Is there 6 numbers on lottery ticket? Lottery ticket 1, 2, 3, 4, 5, 7. Powerball numbers right here. And so you would have an equal and likely chance of winning with all those lottery tickets. Another way to think about it is either you win or lose the lottery, and those are not equally likely because there's only one winning ticket for the whole lottery. So if you just say my sample space of what the outcomes are is I win or I lose the lottery, that's not equally likely. Also, with your team winning, losing, or tying a football game, there are 3 outcomes right there, but they're not equally likely. Ties rarely happen in football. They do happen, but they're not as likely. If you have equally likely things, it's really easy to work with. Like maybe you're doing a drawing and there's 10 names. And you're like, oh man, I really want my name to be drawn. Well, there's one outcome that would have you win. And so we just go right here, 1 over 10. So the probability of you winning, so we can just put probability of an event, and this is the way it's notated, is the probability of event you win is going to be the number of ways that A is satisfied, the probability of winning, you winning. So probability and outcomes of you win over the total number of possible outcomes. There's 10 drawing tickets. Maybe you're there with your family, and now you want to know, we win. So you want to say, man, this is a cool prize, and I'm here with the 4 members of my family, so there's 5 of us out of this 10. It's just one family versus another family for some reason. And so now it's a 50-50 chance. With this right here, you can see the probability we win would be the number of outcomes in which we win over the number of possible outcomes, names that could be drawn out of the hat. So we can do this with dollar bills also. Think about this example if you like. What is the probability of getting a dollar bill with a president's face on it? Now we change our currency every so often, so I want to make these videos what we call evergreen. So I'll let you figure it out. How many bills are there below? And then how many ways are there that you could draw a president's face by drawing a random bill out of a hat? How about this one though? This one gets a little more complicated. If the event is that we want to see getting at least 3 heads, we have right here the sample space of everything that could occur. When you flip a coin 4 times, you could get tails, 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 tails. You could get heads, 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 all these combinations. There's lots of ways to figure this out. We want to see at least 3 heads. Well, if there's 16 possible outcomes, you see over there on the side, we need to figure out at least 3 heads. That's at least 3, at least 3, at least 3, and at least 3, and I think we have one more right there. At least 3 heads. That is going to be 5 ways out of the total. So it's 5 out of the total 16. I believe 0.32, got the math wrong, wait. It's a 16th, which is a half of an 8th. There we go. 0.3125. 0.3125. 5/16. Double check my math if you want a calculator. So with this, we can figure out the probability of something occurring by looking at the total possible outcomes, if all outcomes are equally likely, and the number of ways it can occur, because each of these is equally likely. In mathematics, shown right here, the probability of A is the number of ways A can occur out of the total possible outcomes. We get to the 5 rules on probability now that we will use in this class. There are some more advanced rules, but these are the ones we will use at this moment. First off, probability must be contained between 0 and 1. Something that has a probability of 0 can never occur. I would like to say, and it's sad, but me meeting the real-life Deadpool has a probability of 0. And I'm talking Deadpool, not Ryan Reynolds. That has a probability near 0. I'll take it. But the probability of me meeting actual Deadpool is 0. What am I telling you? That can never occur. Probability 0, probability Brian meets Deadpool, 0. How about the sun will come up tomorrow? Well, that must occur. You could say, what if the sun explodes? Well, at least we wouldn't have to worry about it then. A different world we live in. And with that, the probability right here of something that must occur or will occur is 100%. So probabilities cannot escape the bounds of 0, something that never occurs, to 1, something that must occur. If your parents ever told you to give 110%, that's impossible. Next rule of probability is that the sample space itself must add up to 100%. Now, think about this. This means if we list everything that could occur, it adds up to something that must occur. As in, here's the dice rolls that could occur, and if we look at their associated probabilities, which would each be 1/6, and we add up all these 1/6 because they're all equally likely on a fair dice, well then, we would see right here that we get 100%. So the probability, make sure I have the right amount, right here of a fair dice rolling a number 1 through 6 is 100%. The fair dice will do this. So the probability, and this stands for the probability of the sample space is equal to 100%. Something will occur from the sample space 100% of the time because the sample space is everything that could occur. Next, we get into the complement rule, and this is complement with an E, not with an I. The complement with an I is like you're doing a great job. The complement with an E is not the probability of A. So if you think about the probability that the dice rolls a 5, it would be a 1/6 probability. And if we have the probability the dice does not roll a 5, so if we say probability not 5, then that would be equal to 5/6. And notice why these are complements is that the probabilities add up to 1. So if you say something, I'll either win or lose the lottery, those are complements. This is via the law of excluded middle. You can't have anything in between that. Something either happens or it does not happen. It is A or not A. So you either roll a 5 on the dice or you do not roll a 5. You can't roll a 5, not 5. And because of this, their probabilities are what we say complementary, and they add up to 1. So you either make an A in a class or you don't make an A. Now, confusing things often get people because we say things like, what's the probability of a family having 2 boys in it if there's 2 children? Well, you could say the probability of a boy, let's say, is 48%. The probability of 2 boys. Probability of 2 boys, we'll see this one here in a moment, is going to be 0.48 raised to the 2nd power. More on that with the multiplication rule. But what is the probability of its complement and what is the complement? Well, a complementary family would be any family that doesn't have 2 boys. That's what we're focusing on right now is either your family has 2 boys in it or it doesn't have 2 boys. Any other, and you could maybe even look at, in this instance, we're only looking at families with 2 children, but you could get more extreme and calculate more probabilities from the set of all families that exist. But with this right here, you'd simply do 1 minus this right here, and that would be the probability of a family that does not have 2 boys for a 2-child family. We are going to be using a lot of these rules, especially rule number 4 and rule number 5, when we get to the idea of addition. Addition is simply adding together two probabilities, but when can we do that? The easiest way to do it is when the events or outcomes are mutually exclusive. So mutually exclusive is the same thing as disjoint. These are synonyms. So if I say mutually exclusive, you can just think of disjoint. If I say disjoint, you can think of mutually exclusive. What does mutually exclusive mean, though? Mutually exclusive means if one thing happens, the other thing can't. So let's say you go to the pet store and your parents say, we're going to buy you a dog, a bunny, or a cat. You can't get multiple animals. So looking at this right here, the probability from historic history of cat is going to be 60%. The probability of dog is going to be 35%. And the probability of rabbit is going to be, notice right here we already have a sample space because this adds up to 1. And notice none of it overlaps. So what's the probability you get a dog? Meant to be a dog right here. Probability you get a dog or a rabbit. Dog or a rabbit. To find this out, we need to add them together. Before adding things together, say, my parents said I can only get one animal. If I get a dog, can I also get a rabbit today? The answer is no, which means they are disjoint. When I think of disjoint, I like to think of rabbit as no overlap with dog. If they are not disjoint, what are your parents telling you? In instances of not disjoint, your parents are saying to you, you could get a dog and a rabbit, and then think they are not mutually excluding each other. There's an overlap at times where you go to the pet store and you get a dog and a rabbit at the same time. So all you have to do with mutually exclusive events, if you want to find out the probability they both occur or one of them occurs, is going to be add them together. And the way this would be phrased is, what is the probability I get a dog or a rabbit? So what is the probability I get a dog or a rabbit? You're not saying you're getting both. You're just asking, I get a dog or a rabbit. The probability here would be 40%. Mutually exclusive means it cannot both happen at the same time. So if you're looking at both events, what is the probability that one of them occurs? Another example would be your football team. And if you say my team has a history where they win games, let's say it's the Patriots from years ago. They win 90% of games. They lose 9% of games. They tie 1% of games. What's the probability they win or lose a game? Probability they win or lose. And think, are these mutually exclusive? You have to say, okay, if I just won this game, and we're talking about one game right here, we're not talking about multiple games in a row. We're just saying, I won a game, but I've also lost that game. Like the same game and happened. Now we're saying, could you have lost it? We're saying, can that happen at the same time as winning? You can't win and lose a game at that same game. You can't go to the pet store and get a dog and a rabbit if your parents say you're getting one animal. There's only going to be one outcome to this game that cannot overlap. The probability of winning or losing a game would be 99%. So listen carefully here, we got it. The probability of winning or losing would be 99% given these probabilities. Watch out though with this trick question. What if you say, I have 2 classes I'm taking, and I want to know, we have the probability of an A in chemistry, and the probability of that is going to be 60%, and we have the probability of an A in statistics, and the probability of that is 40%. So what's the probability you make an A in chemistry or an A in statistics? At 100%, watch out, because not how we would solve it. There is a mathematical way to solve this. It goes a little bit beyond, but the probability of A or B, or wrong, there we go. I'll just write or. A or B is going to be equal to the probability of A plus the probability of B minus the probability of A and B happening. And we are not going to solve that in this class. What it would look like is if you took the overlap, which is going to be this right here, and subtracted it off. So in this class, we will only focus on events that do not have overlap. This is not a mutually exclusive event right here. You could get an A in one class and an A in another class. So if you think about the probability of A in chemistry and A in statistics, then you could have both of those occur right there. And so these are not mutually exclusive. Could you get an A in chemistry this semester? Yeah. Could you also get an A in statistics? You could. So you would need to, if you were doing this, subtract off that intersection and see if any problems give you an intersection to subtract it off. It won't be on our test, though. It might be on a Mike Pearson assignment. With this, let's look at the last rule, which will be the multiplication rule. The multiplication rule is what it says it is. We multiply events together. We have here the probability of A and B, and that is found by the probability of multiplying the two events together. And we go back to the word independent. So this means if you know something about B, it would not tell you anything about A, or if you knew something about A, it would not tell you anything about B. One of my favorite examples is it's 30 degrees out today. Do you think it's going to snow? Well, if we look at the probability of it being 30 degrees, would that influence our understanding of whether or not it's going to snow? Days where it is 30 degrees would make it more likely to snow. What if it's 10 degrees? Even more likely to snow. What if it's 90 degrees? Virtually impossible, as far as I know, for it to snow. Those would be not independent ideas. Independent ideas would be something like your favorite basketball team winning tonight and your favorite baseball team winning. You could say, well, maybe that city is doing really well. Well, I don't think they usually get influenced by, I don't think a basketball team wins and then that influences a baseball team to win. So in that instance, your two teams winning would have independent outcomes. Your baseball team winning would not influence your basketball team winning. So if the probability your baseball team wins, go with baseball right here. So we'll go with baseball right there. Baseball right there is equal to, let's say, 60%. And the probability your basketball team winning is equal to, let's say, 55%. We would simply need to multiply those probabilities together. That should be, times it by that, it should be 30, I think 33%, right? Or let's double check our mathematics here. We're going to pull up the calculator. And here we go. 33%, we've done it. So it would be 33% probability right there that your baseball team wins and your basketball team wins. Now, what would be the complement of those? The complement of your baseball team and your basketball team winning both games. Think about this. Either both your team win or what? Either both of your team wins or at least one loses. If we write this out right here, you can see we just talked about this as what we were interested in. Here's the probability of both your teams winning, and here's the complement, at least one team loses, which would have a 67% probability. Now, that doesn't mean both your teams are going to lose. It just means either both your teams win, which has a 1/3 probability. It could happen. Or it's going to be the case that at least one of your team loses. What do we mean by that? Well, it could be your baseball team loses, or your basketball team loses, or both teams could lose. Now, what's the probability both teams lose? Well, now we need to go back to the numbers. And the first number was 40%. Excuse me, I'll tell you the other number. It was 60%, so its complement, 40%. That's the lose for the first team. And the win for the second team was 55%. So its complement is 45%. So now that should be, I think, 18% is the probability of both teams losing. Once again, we'll get the calculator out to check the work. And we do 0.4 times 0.45, and we get 18%. The probability both our teams lose. So the probability the first team loses and the second team loses is 18%. And why are we able to calculate this? Because the first team losing will not influence the second team in any way to win or lose their game. You can write out every probability for each one of these individually, going in and figuring out the probability. This one, like we did, is 18%. What is the probability the first team wins and the second team loses? First team right here wins and second team loses would be this probability. And second team loses and first team loses and second team wins. So you can figure out all these probabilities and write them below and figure out the full sample space of everything that could occur in this idea. As you can tell right here, there's lots of examples to do, and I'm going to write my own example right here. We'll do the luggage example. What is the probability that they lose your luggage on at least one of your 3 flights? Well, if we have right here the probability of lost luggage is equal to 0.03, the first thing we want to think about is the probability of not lost luggage. The probability they do not lose your luggage is 97%. So either they lose your luggage or they don't lose your luggage. Now, the best thing that could happen to us is the luggage is not lost, the luggage is not lost, and it's not lost again, which would be 0.97 to the third power. We're just writing out 0.97 times 0.97, and you should always think about saying these in words right here. They don't lose my luggage, and they don't lose my luggage, and they don't lose my luggage. This is what we would want to occur if we went on a flight. Let's erase this first part of it right here now that we've figured out the probability they don't lose our luggage on all the flights. Because interestingly enough, we're now going to look at the addition rule to see how to solve this. Because it'll be the case that either they will lose our luggage on at least one flight or not lose it on any flights. So if you go on a flight 3 times, you are either going to have your luggage lost at least once, or your luggage will not be lost at all. And since we've listed everything that could occur, this has a probability of 1. And since we said or, that can become addition. So now we go right here and do a little bit of mathematics, and we say, well, let's take not lose it on any flights, which we have right here, and subtract it from the other side of the equation. And we now see that using the addition rule, we've actually found the complement. The probability of losing our luggage on at least one flight is going to be 1 minus not losing our luggage on any flights. So we'll go down here, we'll find out the probability that they do not lose our luggage on any flights. 0.97 cubed. It's basically 91%. I'm going to round it to 91% for brevity. 91%, so there's a 91% probability they do not lose our luggage on 3 flights in a row. And so now we simply substitute in 1 minus 0.91, and now there's a 9% probability that our luggage is lost on at least one flight. That when we go on all these flights, about 9% of the time, rounded it right there, about 9% of the time our luggage will be lost on at least one. It could be lost on one of the flights, any random first, second, third flight. It could be lost on 2 of the flights. Maybe the first one they don't lose it, the next 2 they do lose it, or it could be lost on all 3 flights. But think about this. If there's a 3% probability they lose our luggage, what's the probability it's lost on all 3 flights? It's a different question, much easier one. The probability it's lost on all 3 flights. Write that here so people can follow along. What is the probability it's lost on all 3 flights? Well, simply, that would be they lose it, and they lose it, and they lose it. And there you see the multiply for lose and lose and lose. And I don't think our luggage being lost on one flight would influence it being lost on another flight. Hence, these are independent. So with this right here, simply 0.03 times 0.03 times 0.03. And that would be about there are zeros right here. And then I think we get one more, maybe not. Throw one on, we'll check the work right here. Let's check the numbers and make sure we got it right. See if we added enough zeros. 0.0323, and it is 40. Oh, it's 27 because I did my math wrong. Close, close, we got it almost. But it is 0.2 or 27 at the end there because 9 times 3. And there we go. So with this right here, and I always like to do, if you notice what I do, is I try to do a mental check. I try to do it in my head, and if I get an answer close on the calculator, I believe I've done it correct. If you're wondering why I always do it in my head first and then check the calculator, If both answers concur, I've probably done it correct. And that just gets you some mental prep at doing mathematics. With that, as you can tell, this chapter is a lot more mathy, so practice the mathematics behind it, and you will get it down. Good luck.